Welcome to the next lesson on electrics for Unit 8, and this one is on lighting. And my intention is that you will be able to describe how a bulb emits light and also know the different types of bulb that there are after the end of this lesson. Now, as always, please make sure you've actually got the worksheets with you ready to complete as we work through. And the first light bulb that we're going to deal with, or first type of light we're going to deal with, is the standard incandescent bulb. And on the screen there, what you'll see is there's a double filament bulb, also known as a typical stop and tail bulb. Now, with the bulb image enlarged there, if you have a look at the bottom left of the picture, you'll see there's two contacts. Now, this actual bulb has got two separate filaments, two lights inside it of different powers. This actually operates for our brake light and also operates our tail light or side light at the back. Each one has a separate feed going to it, and that's why there's two contacts on the bottom there. The other thing is, although you can't see it in this image, the actual pin, which is on the silver bit just about midway up, that's a locating pin to make sure that it can only go in one way around, to make sure that each of the contacts on the bottom gets the correct feed at the correct time. So when you put your foot on the brake, it's the actual brake light one that comes on rather than the side light one. If we look to the top at the glass envelope, we can actually see there's 4 bars, 2 pairs of bars coming across. And the topmost one, we can see quite clearly the twisted wire filament. We can't quite see it on the second one just because it's obscured by it. But that's the bit that's actually going to emit the light. So the question is, how does that do it? So what happens to actually get light to come out of there? We apply an electrical current. Now it comes in through, as I say, one of those contacts on the bottom, goes up one of the bars, through the wire filament, down the other bar, and actually earths out through the metal casing at the bottom of the glass envelope. In doing that, there is a small resistance in that twisted wire filament. That resistance causes the electrons to slow down. In doing that, they actually heat the wire, and they heat it up a lot. We're talking about the filament temperature reaching about 2,300 degrees centigrade. Okay, and at that point, it's actually going to get hot enough to start to glow. That's going to actually give us our light source. So what we're doing here is we're converting the electrical energy into heat energy. What else can we convert it into? Think about the effects that we spoke about. You've got a gapped handout on your worksheet. Please complete that now. Pause the video while you do this. Okay, if you go onto the last sheet of your worksheets, you'll also find there's a links page there. In the links page, there is a link to a slow-mo video of a light bulb warming up. Okay, feel free to go and have a look at that at the end of this presentation. Now, with the high temperature involved, even though we're using a tungsten filament, that tungsten is actually subject, or would be subject to air corroding it. So because of that, the actual glass envelope is all the air is evacuated out. It's actually vacuum inside there. It's why if you drop one of these bulbs on the floor, they don't tend to smash and explode out all over the floor. They tend to suck themselves in. You hear almost like a sucking pop noise as one breaks. The filament, though, it still does actually begin to burn off. It still begins to evaporate. And as it does that, what you'll notice on an older bulb is the actual tungsten that's evaporated off will settle on the cooler glass on the outside and starts to blacken that glass as it ages and starts to reduce the light output. So what I'd like you to do now is actually pause the video and go back to your worksheets and actually draw a bulb. Now, it doesn't have to be double filament, it only has to be single filament, but please draw a bulb and label the main parts and give an explanation of how light is given off from an incandescent bulb. Now, whilst a tungsten filament vacuum bulb was actually very good, it gave off quite a lot of light, there was room for improvement. And the next step up from that, specifically for headlamp technology, was the actual move over to quartz halogen bulbs. Now these gave a much better light output, and they did that mainly by increasing the temperature of the filament. They heated it up even more. And we actually got the tungsten filament up to nearly its melting point of around 3,400 degrees centigrade. Now if we did that on a normal bulb, all that would happen is the bulb life would be shortened dramatically. The tungsten would evaporate off, blacken the glass, settle, and we'd actually have a very short life. So with halogen bulbs, what they actually did is used a chemical reaction. Instead of having a vacuum-filled glass envelope, we actually have a halogen gas inside. Now what happens with that is the quartz crystal on the outside reacts with the halogen gas and the heated tungsten and causes that heated tungsten to recirculate back, and instead of setting on the colder surface it can find, it settles back on the hotter surface it can find. That's the filament that's on at that point. So it almost regenerates itself as it works. Now because of this chemical reaction that's taken place, and because the evaporated tungsten is looking to settle on a hot spot, it is vitally important that when you're handling these bulbs, you do not touch the glass or the actual quartz envelope with your hand. Just the oils in your skin will transfer onto the quartz envelope and create a hot spot of its own, and the evaporated tungsten is going to want to settle on the inside of the quartz next to where your fingerprint was. In fact, when somebody's actually done this and it's been run for a while, you can actually see the outline of their fingerprint. You could check who was doing it almost. Now, the particular bulb that's shown here, there are variations on this, but the one that's shown here is a halogen H4. It's a bit of an older design. We don't tend to get this as much anymore, but I wanted to point this out because this, just like the stop and tail bulb, actually has two filaments contained inside it. It's got both main beam and it's got dip. Now if you look closely, you'll actually see that we can see the main filament towards the left, and the dip filament is towards the right, or towards the top of the bulb if you like, or the pointed end of the bulb. And that dip filament's got a shield on it. That shield is to make sure all the light is sent upwards. And when we have a look at a reflector in a minute, you'll see why that is. Now the halogen technology was actually first brought out as a H1 bulb back way back in early 1960s. It didn't really become mainstream, as in on budget cars, until about the late 1970s, early 1980s. But from that point, it was quite a while before our next step. And the reason for the next step is there was still room for improvement on this. Part of the problem we have is the actual light temperature, the actual color of the light that a H4 bulb emits. It's very much towards it looks very yellow compared to some other light sources. And our eyes have been, or have evolved over years to actually cope with daylight and very white light. So manufacturers got to the point of actually looking around for an alternative light source that would actually be closer to natural daylight, which would allow us to see better overnight. So the next step for headlamp lighting was the HID. And this gives an increase in light output, also with lower consumption and a much whiter light. In fact, a standard 35 watt HID bulb gives roughly twice the light output of a 60 watt halogen bulb. These bulbs work very similar to the fluorescent tubes that you see in interior lighting. So let's have a quick look at how this actually works. If you look at the actual diagram, at point 3 we've got a discharge chamber. Now that's actually filled with a couple of gases, xenon and metal halides. And either end of that, number 4, are 2 electrodes. Now by passing a high voltage, and we are talking high voltage here, we can strike an arc similar to the way an arc welder or a MIG welder has an electric arc in it. We get an arc striking across those 2 contacts. and it's that electric arc that gives off the light. So as I said, the actual voltage, the initial voltage that actually puts out is somewhere between 10 and 25,000 volts and up to 20 amps. Now, because of that, we've got our 12-volt battery that's initiating this. We need some sort of transformer to actually take it up there, and that is the actual ballast unit. I'll show you a better picture of a ballast unit on the next slide. So this is a HID ballast. So this is the bit that's actually going to take in the 12 volts, and it's going to boost it up. Now you'll notice at the top there, it's saying caution, high voltage. There is a serious risk of electric shock if you're actually working on these systems when they're live, when they're turned on. So please, 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 if you're ever working on HID equipped cars, do be extremely careful and make sure you know what you're doing before you work on them. So once the electrical arc is initiated, voltage and the current is both dropped down, typically to about 80-85 volts and down to about 3.5 amps. Now the ballast unit supplies this as an AC voltage rather than DC that we saw on the halogen headlight bulbs or the tungsten headlight bulbs. And it's operating at 400 Hertz. Now that means it's actually changing direction, the current is changing direction 400 times a second. And one of the characteristics of these lights is the fact that when the arc is first initiated, they're not as bright as they are once it's actually been running for a short while. They do have a definite warm-up time. If you ever have a chance and you actually turn on one of these lights, you will see it get brighter. If you shine a light against the wall or something, turn it on, the light gets brighter with time. It takes a couple of seconds to achieve full brightness. Now because of this, manufacturers never considered these to be useful for main beam. Dip beam, yes, but main beam, no. Now dip beam can stay on all the time, but main beam, you're going to have to turn it off when other cars come driving towards you, so you don't blind them. Then when you turn it back on, it will take another couple of seconds to get to full brightness. So typically, these are paired up with a halogen main beam. The other thing about this, because we are using an arc, there is a lot of UV radiation, and the glass capsule around it is actually meant to act as a UV radiation shield. You'll also see that depending how you catch these, when you're actually coming towards a car that's fitted with HIDs, you'll notice the actual light can be sort of blue or purple. It's slightly the other way from where a halogen bulb is, slightly towards the yellow side of things. This is more towards the blue-purple side of things as far as the light temperature is concerned. And if any of you are thinking of upgrading your own cars to HIDs, please do bear in mind that it's illegal. These systems have to use an auto headlamp leveling system, and that's just to prevent you dazzling other road users. So that's something that if there's more weight in the car, the headlamps actually adjust their height to make sure that you don't dazzle anybody or any other road users whilst you're driving. A positive thing about these is because there's no filament, this superheated filament that we get in the tungsten bulbs, these actually tend to have a much longer service life. And that is, of course, a very good thing because these bulbs are also a lot more expensive than the halogen headlamp bulbs. The next light source that we're going to take a look at is light emitting diodes, or LEDs. And these are especially constructed to release a large amount of photons outwards out of the LED itself. The smaller ones are the type you might see for warning lights on dashboards, that type of thing. The plastic bulb also concentrates most of the light so it comes straight out through the rounded end. And manufacturers first started using LEDs in the early 90s for dashboard displays, warning lights, that type of thing. And also for illumination of switches, warning lights on switches to tell you that switch is turned on, that type of thing. And pretty quickly they actually found their way into high-level brake lights. And the reason for that is because they've got a much faster response time than a halogen bulb. Halogen bulb has to heat up. These start giving off light as soon as the current is flowing. And the response time from actually turning the current on to seeing light is much faster, nearly 1/4 of a second faster. Now that's really important if we're actually dealing with something as a warning sign to other road users, like a high level brake light, that they may need to slow down as well. That quarter of a second could make the difference between them stopping or parking in your back bumper. Now the beauty of LEDs is they've got a number of advantages over conventional bulbs. They actually use much lower energy. They've got a really long service life, that quick reaction time that we just spoke about, and because they're not very deep, they don't need a lot of depth. We've got much greater freedom of design as to where we want to put them. Think about the BMW Angel Eyes and all the different lighting designs that we now see using LED lighting. But the one thing about them is initially the low power outputs of them stop them being used as headlights. However, back in 2008, the Audi R8 sports car became the first production vehicle to have full LED headlamps. Technology trickles down, and Seat, being from the same group, the Volkswagen Audi group, by 2013 they had an option that included full LED headlights. And these days, you have a look around, you see vastly more cars that have an LED option. And indeed, many that actually come with LED headlamps as standard. Now, there is a step further. I'm not going to discuss it here, but I have included a link for you to have a watch of a video, link to a YouTube video on it. And I think it was BMW that were the first people to bring this technology to the market, and that's using lasers as a light source for your headlights. And I'll let you have a look at that at the end of the presentation. So we've spoken about the light source, and what we need to do though is aim that light source and control it. And that's going to be the job of the lens and the reflector. Now, dealing with the reflector first, if we deal with a plain reflector, there's the light source, or the placement of the light source, is critical. If it's in front of the focal point of the reflector, you'll see the actual light beams are going to converge together like this. When it's on the focal point, all the actual photons are ejected directly out of the reflector. And if it's behind the focal point, then they're going to diverge, as shown here. Now, if you remember when we were talking about the H4 halogen headlamp bulb, the dual filament one, there were two filaments in there, one in front of the other. The first one, the main beam one, is actually positioned on the focal point. The dip beam filament, the one that's got the shield underneath it, is actually positioned in front. Now, because of the shield, all the light source is actually pushed up into the top of the reflector, where it actually bounces off and shines downwards, giving us our dip beam. Now, on older vehicles, like the Mark II Escort featured in the picture here, you'll find that the actual reflectors were plain, but they used a prismatic block lens in front of it to shape and form the actual light pattern. On cars these days, it's far more likely that you're going to see a completely clear front lens mixed with a H&S reflector in the back. That's the actual shape reflector you can see in the picture here. H&S stands for homogeneously numerically calculated surface. Now, you might find that you've got two separate bulbs for both, one for dip beam, one for main beam. If so, you might find that both of them are H&S, or it could be that you have one H&S and one PES, polyellipsoid system dip beam lens. You can also actually get headlights that use two of the PES projector style headlights. Now, those PES lenses may be used with HID bulbs, as in the Honda S2000 shown in the image here, or they could actually just have conventional halogen bulbs in. And both of these styles will actually still have a clear lens on the outside of the headlight. However, when we look at the lens of the rear lights, that rear lens may be coloured. It could be clear, but it may actually be coloured. However, if it's going to be a clear lens, we still need to show the correct colours for legal requirements depending where we're driving, and so we're going to need to use coloured bulbs. Now, in the case of the Lexus style headlamps on the back of the Civic here, that's going to mean using an amber bulb for the indicators and a red for the stop and tail bulbs. Okay, so that's all we're going to cover for now. Please do go back to your worksheets, complete the worksheets, and have a look at those video clips that are attached on the links page at the end of your worksheets. Thanks very much for watching. See you soon.